Good day again. Today we are going to discuss DC circuits, which is chapter 26 from the Giancoli book. And DC stands for direct current. And so what that's basically saying is that there's a voltage source that is steady. It's constant. The positive and negative terminals don't shift the way they do in an alternating current, but you have the current in one direction and it's constant. And so the source of the DC voltage, or rather the source of the voltage, is called an electromotive force or an EMF. So sometimes instead of delta V, you'll see a fancy looking E. And so the fancy looking E stands for EMF. So our lecture today is basically covering three topics. The first is resistors in series and parallel. So when resistors are in series, they're connected one after the other. So the same current flows through all of the resistors. So I1 is equal to I2 is equal to I3, and if you have more resistors, it goes on from there. But they're all equal to the total current that's feeding into that segment. But the potential differences are adding. So you have a current feeding into that segment, and you have a potential difference feeding into that segment. So the total voltage that comes in is equal to the sum of the voltages across each of the resistors in series. And with a little bit of math and applying Ohm's law, what you get out of that is that the total resistance, or the equivalent resistance, or the effective resistance, you'll see all three terms used, is equal to the sum of the individual resistances. So when you're connecting resistors in series, the total resistance is the sum of the individual resistances. So it's the opposite of capacitors in series. And so with resistors in parallel, that's also the opposite of with capacitors. So when you have resistors in parallel, the current splits into multiple branches. And so each branch gets some of the current. So the total current feeding into that segment is equal to the current through the first resistor plus the current through the second plus the current through the third. So I1 plus I3 plus I1 plus I2 plus I3, plus the current for how many other resistors you're connecting in parallel. The voltage is the same across each branch. So that's just like is the case with capacitors, that each branch has to have this, in a parallel segment, has to have the same potential difference as the potential difference that fed into that branch of the circuit. And again, you do a little bit of math with that, and what you get is an inverse sum relationship. So resistors in parallel are like capacitors in series. So 1 over R total is equal to 1 over R1 plus 1 over R2 plus 1 over R3, and so on and so on and so on. So the total resistance is less than any individual resistance. Another way of thinking about that is thinking about the relationship from the last chapter between resistance and resistivity. So R is equal to rho times L divided by A. And so you can think when you're connecting resistors in series, you're increasing the length, which increases the resistance. When you connect resistors in parallel, you're increasing the cross-sectional area, which decreases the resistance. So, it's another way to visualize what's going on. And so now we're going to move to an example. So you have a 650 ohm and a 2200 ohm resistor that are connected in series with a 12 volt battery. So what is the voltage across the 2200 ohm resistor? So let's set this up visually. So they're connected in series, and you have one power supply. So let's set up the whiteboard. So you have your power supply, which in the problem is 12 volts. And so you have your circuit, and you have two resistors. And so we have R1 is equal to 650 ohms. And R2 is equal to 2200 ohms. So what you want to do is find the voltage across the second resistor. We'll call that delta V2. So what do we know? Well, we can apply Ohm's law to the total circuit, but we can also apply Ohm's law to each resistor. So we know that delta V total is equal to I total times R total. Now, we don't know what I total is yet, but we can figure out R total from what we're given. So R total is the sum of the two resistors because they're connected in series. So that's 2,850 ohms. So to find I total, that's equal to delta V total divided by R total. So this is basically a two-step problem. So we can calculate this. So that's 12 volts, and you're dividing by the sum of these. So that's 2850 ohms. And so how much current is that? So that's 12 divided by 2,850. That's, we will do two significant figures. So that's 4.2 times 10 to the negative 3 amperes, or 4.2 milliamps if you prefer. So that's I total, but it's also equal to I1 and I2. Remember, it's a series circuit. So we can apply Ohm's law again, this time to the second resistor. So you have delta V2 is equal to I2 times R2. Well, I2 is just the total current. Again, it's a series circuit. It doesn't branch. So that's 4.2 times 10 to the negative 3 amperes. And you're multiplying it by the second resistance, which is 2200. And that's ohms. So you may still have the answer from the last problem in, so you just multiply that answer by 2200, and that gives 9.3 volts. And then the resistance, or delta V1, is just the difference between the two. So you can multiply the current by this voltage, but it's probably easier to just subtract 9.3 volts from 12 volts, and that would give you 2.7 volts, assuming you needed to calculate R1 as well. So that's what you do here. So now we're going to move to another example. So suppose, this is number 9 in the book. Suppose that you have a 9.0 volt battery and you wish to apply a voltage of only 4.0 volts. Given an unlimited supply of 1.0 ohm resistors, how could you connect them so as to make a voltage divider that produces a 4.0 volt output for a 9.0 volt input? So the key to this is the fact that they're 1 ohm resistors doesn't matter. Basically, you can apply resistors in whatever combination you want. So this is more of a qualitative problem than anything else. Since you don't actually know the current, and you don't actually know how much resistance you have in your load. So you're applying your voltage of 4.0 volts to your load, which is the useful resistance, the useful part of the circuit, but you're removing 5 volts from that. So what you can do is you're connecting your combination of resistors, called the voltage divider, in series with your load. So just to visualize what's going on here. So again, the numbers don't really matter. You know that you have 9.0 volts coming out. And you have one segment that's your voltage divider, and one segment that's your load. And again, the load is the useful part of the circuit. But the load only needs 4 volts. So delta V over the load portion is 4.0 volts. You don't know what the load is or what current you expect to go through it, but all you know is you only need 4.0 volts going over the load to have it do whatever it is that you want it to do. So the voltage divider, and we will do an experiment that has a voltage divider. When we get to what we call the meters lab, you will see a voltage divider. That is going to get the remaining 5 volts. And so you have this segment connected in series with the load segment. So you have a combination of 1 ohm resistors making up the voltage divider, and how those resistors are connected ultimately depends on what how much resistance or total or equivalent resistance you need so that the voltage across this segment of the circuit is 5.0 volts. So you could have resistors connected in series, you could have resistors connected in parallel, you could even have some combination of the two. You're not given enough information to do more than that with it. But you have different segments of the circuit. And again, Ohm's law applies over individual segments of circuits, and the relationships with series and parallel also apply over given segments of a circuit. So you can have a segment with 2 resistors in parallel connected in series with a segment that just has a resistor. So you may need to figure out the mathematics of how they go together, but you figure out the total or equivalent resistance of each individual segment and then figure out how they combine. So you start at the start small and work your way up to the big picture. So getting back to our lecture notes, now we're going to get to something called Kirchhoff's rules. Kirchhoff's rules may seem complicated, although I imagine if some of you are EE students, you've probably already seen it. But Kirchhoff's rules might seem complicated at this level of physics. Certainly it's a lot of algebra to know, but it's a formalism that makes the mathematics of working with very complicated circuits easier. That the more complicated the circuit is, the more simple, at least in a relative sense, Kirchhoff's rules make doing the math. And of course, if you have many equations with many unknowns, you can solve them with the computer if you'd like. There's plenty of coding out there that can do that for you. We're going to stick to 3 equations with 3 unknowns. We're not going to do anything more than that, but you should be able to do that much out by hand. But anyway, so how do you analyze the current in different branches of a complicated circuit? And Gustav Kirchhoff, a German scientist in the 1840s, came up with a basic set of laws that govern the current and voltage in complicated circuits. So you have the junction rule. The sum of the currents entering a junction must equal the sum of the currents leaving a junction. So that's fairly straightforward. The current going into a junction equals the current going out. The loop rule is quite a bit more complicated and a bit less intuitive, certainly at the introductory level. For the loop rule, the sum of the voltage rises and voltage drops across all the elements in a closed loop must equal 0. Well, what is a voltage rise? Well, what you'll need to do is draw the direction of the loop. So you're going to do a closed loop. You want to give it a direction. And so if you have a power source and the current is going out of positive and into negative, that's called a voltage, and rather the loop arrow is going out of positive and into negative. That's considered to be a voltage rise. If it's working the other direction, it's called a voltage drop. With a resistor, if the current arrow and the loop arrow are going in the same direction, so I'll show this visually in a second, that counts as a voltage drop. And if the current and arrow and the loop arrow are pointing in opposite directions, that counts as a voltage rise. So that seems a little bit complicated right now, but I will visualize this in a couple of seconds. So the first step in applying these rules is to determine which directions are positive and which directions are negative. And so you assign a direction to each current and assign a direction to each loop. So why don't we do that right now? I'll give a basic circuit so you can see what's going on. So you have delta V1 and you have R1. So that's R2. And we'll have a delta V3. We'll call it delta V3 because it's on the third branch. So this is a basic circuit. So how would you apply Kirchhoff's rules? So the first thing we're going to do is set directions of the currents. So we're going to have I1 going through R1, I2 going through R2, and I3 going through R3. So let's draw current arrows. And when in doubt, draw the current as coming out of the power source. So if you've got an EMF source, you can set the current arrow like that. So that's I1 coming out of the positive terminal. And we can do the same thing at the bottom. So that's I3. So on the left side, so you have I3 going up and you have I1 going up also. We want to figure out what direction to assign to R2. So this doesn't really help us much. But for the sake of simplicity, we'll have I2 pointing to the right. And so you have two junctions. So you assign directions of your currents. You also want to assign directions of your loops. So we have two loops, one for the top segment. And again, it's easy to draw the directions of the loop if you have the option of doing so, to do it out of the positive terminal of a power supply and into its negative terminal. So this is loop 1. And then on the bottom, coming out of positive and into negative, so this is loop 2. So let's say we're given the voltage values and we don't know what the current values are, and we're asked, and we're given the resistances. So we're given the delta V's, we're given the R's, we're not given the I's. But we have enough information to solve that. And so here's how you do it. So the first equation is the junction rule equation. The junction rule says the total current going into a circuit is equal to the total current going out, or into a junction, is equal to the total current going out of a junction. So let's look at this junction here. We have I2 and I3 coming in and I1 going out. So that says that I2 plus I3 is equal to I1. So that's nice and simple. So that's the junction rule. And we'll give that by the letter J. So that's one equation with our three unknowns. Now, if you go to the other side, you see there's a second junction, but if you do apply the junction rule there, you see that you get the exact same equation, that I1 is coming in, I2 and I3 are going out. So it's still I1 is equal to I2 plus I3, but you already know that. And in general, if you have n junctions, speaking algebraically, then you'll have n minus 1 equations for the junction rule. So if you have two junctions, you'll get one junction rule equation out of that. And so now you have two loops. And so loop 1, and again, the basic rule says that the sum of the voltage rises and the voltage drops equals 0. So how does that look? So we'll start with the EMF source, delta V1. So this is loop 1. We've drawn the loop so that it's coming out of the positive and into the negative. So that's called a voltage rise. So that's delta V1. Now we get to the first resistor. So you look at the current arrow and you look at the loop arrow. If they're going in the same direction, so the loop arrow is going right to left on the top, and so is the current arrow I1. So they're pointing in the same direction. So that is a voltage drop. So that becomes minus I1 R1. But we're still not done. The loop continues down here, and you see you have I2 going through R2. And the bottom part of the segment, the loop arrow is going from left to right. The current arrow is also going from left to right. So when the loop arrow and current arrow match up, it's a voltage drop. You have to subtract. So that's minus I2 R2, and that equals 0. So that's the first loop rule equation. Now we're going to loop 2. And we'll notice this is a little bit trickier, but we'll start again at the power source. So that's here, and you see we've drawn the loop so that it's coming out of positive and into negative. So the EMF source is a voltage rise, so that's delta V3. The current arrow is pointing left to the right on the bottom. The loop arrow is pointing left to the right on the bottom. So it's a voltage drop. So that's minus I3 R3. And then you get up to R2. But notice what happens here. The loop arrow is pointing to the left at the top part, but the current arrow is pointing to the right. So they oppose each other. So this is actually a voltage rise in loop 2. So you have to add I2 R2. And that gives you 0. So the voltage rises and the voltage drops add up to 0. So now you have three equations, and again, if you know you're given the voltages and you're given the resistances, you have still have the three unknowns for the current, but you have the three equations. You can now solve for the current. And you can solve this any way you want. You can do it algebraically. You can use row reduction. You can do this on computer if you want. In fact, the more complicated the more equations involved, the easier it is to set up some sort of coding program on the computer and have it find the answer for you. But that's basically how this works. So for the exams, if you get a Kirchhoff's rules problem, it won't be more than three equations and three unknowns to work with. So, okay, let's get back to our lecture slides. So the sign conventions for current, it's positive if the current in fact goes in the direction you assign it, negative if the current goes in the opposite direction. So let's get back to the whiteboard for a second so you can see what's meant by that. Now, if you set up the equations just like this, it's possible that one or more of your current values will be negative. In fact, I2 looking from this could go either way. It's not a wrong answer if you get a negative value. It simply means that the current is actually going in the opposite direction that you assigned it. And again, that doesn't necessarily mean, if the math is done correctly, that does not mean you got the wrong answer. You just need to say, well, the current, well, I drew the arrow to the right, but the current is actually going to the left. So let's get back to our slides again. Now for voltage across the power supply, again, positive if the assigned voltage loop direction points out of positive and into negative. And usually that's how you assign the loop, figure out how to assign the loop directions anyway. Negative if the voltage loop direction points into positive and out of negative. Sometimes that might happen if you have a complicated combination of power supplies. You may get something like that, but usually you're going to draw the loops so that they're out of positive and into negative. And across the resistor, it's a voltage drop if your loop and current arrows are going in the same direction. And it's a voltage rise, or it's positive, if your loop arrow and current arrow point in the opposite directions. And again, sometimes that might be necessary depending on how you set the problem up. And it's not, as long as you can keep track of your positives and negatives, it's not that big a deal. Your choice of the current directions and the voltage loop directions is ultimately arbitrary. But if you follow these rules, you should get the correct answer. And again, if you get currents that are negative, it means they're actually pointing in an opposite direction to what you originally assigned. Okay, so let's get to an example. And so I need the textbook for this one. Hold on one second. Okay, so the problem says for the current shown in figure 2647, find the potential difference between points A and B. The voltages are 1.5 volts and each resistor has 130 ohms. So let's set this up first. So we'll go to the whiteboard and draw this out. So we can clear this. And so we have our circuit. And so we have multiple power sources. And so we have a value R there. Not so easy to draw those sideways. And so we have point A and point B. We have 4 resistors. And we have 2 1.5 volt batteries supplying the EMFs. And so we know that R is equal to 130 ohms. And we are asked to find the potential difference between points A and B. Now, you might look at this and guess what the answer has to be. But for the sake of argument, we'll do it out the mathematically formal way, because if the values for R were different from each other, it wouldn't work out so simply. And so you'd need to be mindful of that. You would need to set things up. So we have one loop. So, and both EMF sources point the same way. And so you have one loop, and so we'll draw the loop like that. And so there are no junctions. There's no place where the current branches off. But we'll draw the current arrows in the same direction of the loop, or the current arrow in the same direction of the loop, because there's no reason not to. And then we apply the loop rule. So voltage rises minus voltage drops is equal to 0. So we have 1.5 volts minus, starting from here. So again, the loop is coming out of positive and into negative, so that's a voltage rise. So 1.5 volts minus I times R, and we know what R is, minus I times R again, plus another 1.5 volts, minus I times R, and then minus I times R. So we're subtracting I times R 4 times. So we'll set it up like that. So 1.5 volts minus 4IR plus 1.5 volts equals 0. So again, the voltage rises and the voltage drops. Here the resistors of the voltage drops, the current and the loop arrow point in the same direction. So you're subtracting I times R in all those cases. And the loop arrow goes out of positive and into negative for both batteries. So that's a voltage rise in both cases. So we have 4IR is equal to 3.0 volts. And so I is equal to 3.0 volts divided by 4 times R, and R is 130 ohms. So this tells us the current, at least to 2 significant figures. And so that's 0.023 amperes, or 23 milliamps. But that doesn't solve the problem. You're trying to figure out the voltage between point A and point B. So we know which direction the current is going. So we follow the direction of the current. So when you're following the direction of the current, the resistor is a voltage drop, and the power supply, assuming it's going in the assuming the current is going out of negative into positive, is a voltage rise. So the potential difference between points A and B is equal to negative I times R plus 1.5 volts. So negative I times R plus 1.5 volts minus I times R. And you can probably see from doing this, and if you do the math out to 2 significant figures, you'll get the correct answer. So so that's you have 1.5 volts minus 0.023 times 130 minus why is this not looking right? That's 3 divided by 4 divided by 130. Okay, yeah, I made a mistake. Forgot to divide by 4 up here, so that was a boo-boo on my part. This answer is 5.8 milliamps, or times 10 to the 3. So that explains why I wasn't getting it right when you do the math. But you can plug these numbers in here, and if you do that, you get 0. So again, using this value of the current, these values of the resistance, and 1.5 volts to 2 significant figures, you should get 0. And again, the reason is because the resistors are equal. You get the same amount of voltage going across each resistance. So not only are they equal, but the power supply or the power sources are equal as well. But if there was a difference between, if the R values were different or the delta V values were different, you would have to go through this more methodically like it's done here. You need to figure out the total current and then figure out the voltage drop going from A to B. And again, If you know which direction the current is pointing, it's straightforward. So you subtract I times R, and if the current is pointing into negative and out of positive, you're adding the voltage source. But in this case, because of the symmetry of the problem, the voltage difference between points A and B is equal to 0. So now we're going to do another example. And so this is determine the magnitudes and directions of the currents through R1 and R2 in figure 2651. So this is at the bottom of the page, 701. But let's look at this, and again, we'll visualize. So we'll set this up, and we've got 3 branches. So it's not all that different from the example I showed before. So V1 is equal to 9.0 volts. And so you have on that top segment an R1 equal to 22 ohms. At the bottom, you have a power supply that we're calling V3, and that's equal to 6.0 volts. And you don't have any resistors in that portion of the segment. And then in between, you have R2 is equal to 18 ohms. And you're asked to find the magnitudes of the currents through R1 and R2. So we will label this current I1. We will label this current I3. And again, we're not really sure what direction or what direction to give the current arrow for the middle segment. But we'll draw I2 to the right. And again, if it's correct, or if it's the correct direction, then you get a positive value for I2. If it's an incorrect direction, you will get a negative value for I2. So again, we have our junctions. And so there are 2 junctions, which means you have 1 independent junction rule equation. So if you look on the left, I1 comes in, I2 and I3 go out. So I1 is equal to I2 plus I3. So that's the junction rule. Now for loop 1, we will draw, again, we'll draw it coming out of positive and into negative. So we'll call that loop 1. And so V1 is a voltage rise, again, because out of positive into negative. So V1, here we have the loop arrow at the bottom part of the loop is pointing to the right. The current arrow for I2 is also pointing to the right. That's a voltage drop. So that's minus I2 R2. And then you curl back around, and again you have at the top of the loop, the current is pointing to the left, or rather the voltage loop is pointing to the left at the top, and the current arrow is also pointing to the left. So that's another voltage drop. So that becomes minus I1 R1. And again, the sum of the voltage rises and voltage drops equals 0. Now we're going to do the same thing below. Again, we'll set up the directions of the loop arrow so it's coming out of the positive and into the negative. So here we have V3. The loop is coming out of the positive terminal of V3. So that's a voltage rise. Now you get to the top, because there's no other resistor except R2. Your loop arrow is pointing left in the top part of the loop, but the current arrow is pointing right, so you have to add I2 R2. And that equals 0. So here we know the resistors we don't know the currents. And we're basically asked to solve for I1 and I2. And you could probably already see from looking at the loop 2 equation that I2 has to be negative, that I should have drawn the arrow in the other way. But again, if you do that in a problem, you're not getting the answer wrong. You're just, the negative sign means that I2 actually goes in the opposite direction to what you assigned it. So that's negative V3 divided by R2, doing the algebra from here. And so that's negative, and that's 9 divided by 18. So it's negative 9.0 volts divided by 18 ohms. And so that's an easy enough answer. Negative 0.50 amperes. So that's I2. And if you look at the loop 1 equation, since we now know I2, there's only one value for there's only one unknown, and that's I1. So you have I1 R1. Just adding that to both sides of the equation is equal to V1 minus I2 R2. So you can write this then as I1 is equal to V1 over R1, just dividing both sides by R1, minus I2 R2 over R1. So with that, you have V1 divided by R1. So that's 9.0 volts. Oh, excuse me. I made a mistake here. That's not 9 volts, it's 6.0 volts. And so instead of 0.50, that becomes negative 0.33 amps. So you have, so negative 0.33 amps. And so that's going to the left. So V1 over R1, so that's 9.0 volts divided by R1, which is 22 ohms, minus, or 22 ohms, excuse me, minus I2, but don't forget I2 is negative. So you're subtracting a negative, which is effectively adding a positive, and then times R2 over R1. So that's 18 ohms over 22 ohms. And so you plug those into each other. You get 0.68 amps. So that's how you solve that problem. And you can figure out I3 from this if you wanted as well. I3, the problem doesn't ask for it, but I3 is equal to I1 minus I2. So that's 0.68 amps minus negative 0.33 or plus 0.33. That gives 1.01 amps in I3. And so that's how you would solve that. And that brings us to the last topic we're going to talk about today. In fact, it's the last topic we're going to talk about in electricity. Everything from this point on is magnetism. So the last 4 chapters deal more specifically with magnetism, although electricity comes in quite a bit. What you'll find is that magnetism and electricity are actually very closely related to each other. So we're going to do a little bit of calculus here. So we're going to look at what are called RC circuits, which is a resistor and a capacitor connected in series. And if you've done the capacitors lab, you saw one of the consequences of plugging in a small resistance is that you could see the charge or discharge of the capacitor over in real time. You can see it happening in real time. If there was essentially no resistance in the circuit, the process of charging or discharging the capacitor would happen more or less instantaneously. But the time it takes to charge or discharge a capacitor is, in principle, measurable. And so what we're going to do is define a time constant tau as being equal to the product of resistance times capacitance. Now, the value of the ohm depends on how you define the ampere. The value of the farad depends on how you define the ampere. But the product of resistance and capacitance does not depend on how you define your current or your unit of current. It's always going to be in seconds. So most of the quantities we talk about and their values depend on how you define the ampere, but some of them don't. And this is an example of one that doesn't. So we're going to derive the relationship of the charge that builds up in the capacitor as a function of time. So how does that look? So let's go to the whiteboard, and hopefully we will have enough space to do this. So we have a basic RC circuit. And we have a resistor and a capacitor in series. So, and remember, the definition of capacitance is C is equal to Q over delta V, so that Q is equal to C times delta V. So that'll come into play later. So in a series circuit, the voltages add up. So the total voltage is going to equal the total voltage across the resistor plus the total voltage across the capacitor. And that's true at any point in time while the circuit is charging. So you can write delta V as being equal to the voltage across the resistor, which is just I times R, plus the voltage across the capacitor. And again, you can also write this equivalently as delta V is equal to Q over C. So you can write this as Q divided by C. Now, if you know the charge is a function of time, then the current is just the derivative of the charge. So you can write this as R times dQ over dt, the derivative of the charge with respect to time, plus Q divided by C. So if you remember that lab experiment, the current probe measured the current as a function of time. Once the capacitor got fully charged, that current went down to 0. So the current, in addition to being a measure of the amount of charge that's flowing through any point in the circuit as a function of time, it's also a measure of the amount of charge that's building on the capacitor as a function of time. And so you have this differential equation. And let's now figure out how to solve it. So we're going to define, we're going to bring the Q over C term to the other side of the equation. So we're going to subtract Q over C from both sides. So the delta V minus Q over C is equal to R dQ over dt. So we're going to let U equal delta V minus Q over C. The differential of U with respect to time, it's a DC circuit, so the voltage across the power supply is not changing. So d over dt becomes minus 1 over C times dq over dt. So you can write dq over dt as being equal to negative C du over dt. So now let's plug this into the equation. So we have U is being equal to R times dq over dt. So we have negative RC du over dt. Just putting in this value of dq over dt in here. So we're going to isolate the u terms on the right side and bring the t term over and the RC term over. So we multiply both sides by dt, divide both sides by RC, and also divide both sides by u. So in fact, we'll bring the negative over as well. So negative dt over RC is equal to du over u. Now we can integrate this. So we're going to a time t, and so we're going from time t is equal to 0 to a time t. So we're going to integrate. So the value of u at t equals 0. Well, if we're charging the capacitor, then we're assuming it's uncharged initially, so that this becomes delta v. U is just delta v at t equals 0. But then it's delta v minus q over c. So at a time t, it's going to equal this. And so q is a function of t, and delta v is constant. So these are easy integrals to integrate. This simply becomes negative t over RC. And that's equal to, now the integral of delta u over u is just the log of u. And again, you're evaluating that at delta v and at delta v minus q over c. So you can write that. Remember, log of a minus log of b is equal to the log of a over b. So this becomes the log of delta v minus q over c divided by delta v. And now we can take the exponent of both sides, take e to both sides to remove this natural logarithm. So e to the negative t over RC, and remember, the product r times c is the time constant tau, is equal to delta v minus q over c divided by delta v. And so we want to isolate the q. So this becomes, we multiply both sides by delta v. So that's delta v e to the negative t over RC is equal to delta v minus q over c. And we'll write that as a function of t. So I'm going to erase what I have on the left side here. And we'll finish the problem. So you can then reverse these two terms. So q as a function of t over c is equal to delta v minus delta v e to the negative t over RC. And so we can write q as being equal to c times delta v multiplied by 1 minus e to the negative t over RC. So just factoring out the delta v terms here and multiplying by c. But what is c over delta v? Well, that is the charge q that happens when the voltage across the capacitance is equal to the voltage across the power supply. So in other words, at the point when you stop charging. And so that is the maximum value of q times 1 minus e to the negative t over RC. So that's Q as a function of time. And so that's for a charging capacitor. The current as a function of time is equal to dq over dt. So that's equal to, well, this term is constant. It doesn't come into play. So it's only the bottom one. So you have minus e to the negative t over rc, but then you're multiplying by -1 over rc. So that becomes positive Q max over rc times e to the negative t over rc. And you can write that. Remember, Q max over c is just the voltage across the power supply. Delta V over R is the maximum current, and that happens if t is equal to 0. So that becomes I max times e to the negative t over RC. So let's erase the right side now so I can show you this, how these look graphically. And this is for a charging capacitor. The mathematics is somewhat similar for a discharging capacitor, but the end result is not the same. We'll go over the end result in a couple of minutes. But you have Q versus T. And so we'll draw a horizontal dashed line for Q max. And so you start at 0, and you keep approaching the dashed line, but you never actually get there. And so that's how Q max looks. And then you have I max versus T. And so you're starting, or I max, you start at I max at T equals 0, and you have an exponentially decaying function looking something like that. So that's how they look. And I'll go over a little bit of the mathematical relations here. So at tau equals 1, Q is equal to maximum Q times 1 minus e to the negative 1, which is approximately equal to 62%. At 3 time constants, Q is equal to, or the 62% times Q max. And then for T, tau is equal to 3, that's 1 minus e to the negative 3, that's approximately 95% of Q max. So you can think of it as that after 1 time constant, you're it's 62% of charge. Between tau equals 1 and tau equals 2, you've gone 62%. You've gotten 62% of the remaining charge. And between tau equals 2 and tau equals 3, you've gotten 62% of the remaining of whatever charge you had left at tau equals 2, and then so on. So basically, after an interval corresponding to 1 time constant, you've accumulated 62% of whatever charge there was left to accumulate. And the current, by contrast, drops by 62% over each time constant. So at tau equals 1, it's 38% of its initial value. At tau equals 2, it's 38% of 38% of its initial value. At tau equals 3, it's 38% of 38% of 38%. And so you see how that goes. So let's get back to the lecture slides. So for a charging capacitor, Q is equal to the maximum or Q as a function of time is equal to the maximum charge times 1 minus e to the negative t over RC. Again, the product of R times C is the time constant. So the bigger the time constant, the longer this takes. Q max is equal to C times delta V max. So the capacitance times the voltage coming out of the power supply. For a discharging capacitor, it's Q is equal to Q max e to the negative t over RC. So it's an exponentially decaying function. It looks like, and for both cases, I is equal to I max times e to the negative t over RC. I max from Ohm's law is equal to delta V max divided by R. So for a charging capacitor, Q is equal to the maximum Q times 1 minus e to the negative t over RC. For the discharging capacitor, it's exponentially decaying. In both cases, the current is exponentially decaying. And again, if you remember the lab with the capacitors, whether you were charging or discharging, you had a very sharp value initially once the event started, but that value decayed down to 0, or down to approximately 0 over a relatively small amount of time. And we will do another experiment where we look at that a bit more directly. So one more example, and then we're done for this lecture. So in figure 2658, so we're moving on to page 702 now, the total resistance is 15.0 kiloohms. The battery's EMF is 24.0 volts. If the time constant is measured to be 24.0 microseconds, calculate the total capacitance of the circuit and the time it takes for the voltage across the resistor to reach 16.0 volts after the switch is closed. So let's set this up. Again, back to the whiteboard. And so we'll clear the screen. The first thing we will do is set up the diagram. So we have our power source here. We have a switch that we'll call S. And so when the switch is open, the circuit is not fully connected and nothing happens. So we have our capacitor here, but we also have a resistance. So it looks something like that. And we are given, the total resistance is 15.0 kiloohms. We know the battery's EMF is 24.0 volts. And the time constant, tau, is measured to be 24.0. Right, they're both 24.0? Yes, 24.0 microseconds. And that's microseconds 10 to the negative 6. So the first thing we're asked is the total capacitance of the circuit. So we're given tau, and we're given R. So tau is simply RC, so that C, the capacitance, is equal to tau divided by R. And so C is equal to 24.0 times 10 to the negative 6 seconds. And the resistance is 15.0, and that's kiloohms. So that's 10 to the 3 ohms. So you have 24 times 10 to the negative 6 divided by 15E3. That gives 1.60 times 10 to the negative 9 farads, or 1.60 nanofarads. Either works. So that's the easy part of this problem. The harder part is the time it takes for the voltage across the resistor to reach 16 volts after the switch is closed. So we have our basic equation, and it's a charging circuit. So that's Q is equal to Q max times 1 minus e to the negative t divided by tau. Since we're given tau, we'll write it like that. Now, we multiply both sides by C. So Q times C is the voltage across the capacitor. Q max times C is the maximum voltage, which is the EMF. So that's just the fancy looking E, times 1 minus e to the negative t divided by tau. And now we want to solve this for t. So the first thing we're going to need to do is divide both sides by the fancy e. So delta v over e is equal to 1 minus e to the negative t over tau. And we want to isolate the exponential term. So we can add this term to both sides and subtract this term from both sides, so that we get e to the minus t over tau is equal to 1 minus delta v over fancy e. Now we take the natural log of both sides. So we're kind of working backwards from our derivation. So you take the natural log of this side, it's just negative t divided by tau is equal to the natural log of 1 minus delta v over fancy e. So we can then solve for t from that. So t is equal to negative tau times the log of 1 minus delta v over fancy e. Don't worry about the negative sign. This number is going to be less than 1, and the natural log of a number that's less than 1 is going to be negative. So the negatives will cancel out, and you have a positive number. So that's negative t, which is 24.0 microseconds, times the natural log of 1 minus delta v over e. So delta v, we're asked for how long it takes for the voltage across the resistor. So the voltage across the resistor is 16 volts. The voltage across the capacitor is 8.0 volts, because the sum is going to add up to 24 regardless. So this is 8.0 volts divided by 24.0 volts. And so you plug those in. So you're basically taking so that's 1 minus 1/3, or 2/3, and you're taking the natural log of 2/3. And that's a negative number. It's about negative 0.405. And you're multiplying that by the 24 microseconds. And don't forget, the negative signs cancel out. So this becomes 9.73. And you can leave it in microseconds, because your answer starts in microseconds. So for the voltage across the resistor to be 16 volts, that means the voltage across the capacitor is 8 volts. So it's about 1/3 charge. So you know it's going to be less than one time constant. One time constant would be about 62% charge. So it's definitely less than that, and quite a bit less than that. So it takes 9.73 microseconds, less than half of a time constant, to get to 1/3 fully charged. And so there you have it. And so that's all we're going to cover today. We'll go over some more advanced problems in the recitation. And then this is the last chapter. No, this is not the last. This is the last chapter for electricity. This is not the last chapter for exam number 3. We're going to do the first magnetism chapter, chapter 27, as part of exam 3. So Again, as always, if you have any questions, don't hesitate to email me. Otherwise, I will talk to you soon.